So to get a grasp of volume by cross sections, let's take a look at a website where you have videos that describe how these shapes are formed. Let's take a look at the pyramid shape. So if you stack a bunch of squares one on top of the other, you end up with a pyramid shape. If you could find the volume of each square, then you could find the volume of the pyramid. That's a finite number of squares, though. We want to be able to find the volume of the pyramid exactly. This picture shows how we can do it by approximation, and so we end up having to find the volume of, find the area of the square, and then integrate that, as we saw in our previous video about the idea, the concept behind volume by slicing. If we could find the area of the square and then integrate that, we could find the volume of the shape. Here's another video where we have the shapes being not squares, but them being semicircles. If we could find the area of the semicircle, right here would be a function of x. This function is the y equals root x. So we'd have to find the area of the semicircle. The semicircle has a diameter that runs from the x-axis up to the function. And so you generate these cross sections that way, and we want to find the volume of this shape. Let's do one more video here. This time the shapes are, this is a sine x from 0 to pi. This time the shapes that create the actual 3D shape are equilateral triangles that have one side length of the triangle running from the x-axis up to that curve. And that's what the three-dimensional shapes looks like. So we're going to find the volume of these shapes. It's called volume by cross sections. It depends on us being able to find the area of equilateral triangles, the area of semicircles, the area of squares. And so let's take a look at that. First up, let's look at the area of a square. If the side length is s, then the area of the square is just going to be s squared. No mystery there. If we have a semicircle, like we saw in the picture, where the diameter was length s, we would need a formula for the area of this semicircle. Well, you know, it's a circle. It's half of a circle, so we need the radius. And if the diameter is s, then the radius is half of s over 2. The formula for the area would be not pi r squared, but half of pi r squared. So we square the s over 2, and we get s squared over 4. Times it by pi over 2, and we get this formula for the area of a semicircle that has a diameter of length s. Pi over 8 times s squared. Okay, how about an isosceles right triangle where the leg length is s? Sometimes the cross-sectional shapes end up looking like this. So it's isosceles, 45, 45, 90 right triangle, but basically it's a triangle that has a base of s and a height of s. So the area is 1/2 of x squared. 1/2 the base times the height, or half of the square area. It gets much more difficult if you think about it as an isosceles right triangle, but the hypotenuse is s. Then it becomes much more difficult. We need the base and the height. The base is here, and the height is here. But we know they're the same. It's isosceles, so we know they're the same. So let's first just call them x. They're both x. Okay, this guy being your base, and this guy being your height. We do 1/2 the base times the height. So we need x, but we need it in terms of s. And so we can use Pythagorean theorem. X squared plus x squared should be s squared. Or twice x squared should be s squared. Or x squared should be s squared over 2, divide by 2. Take the square root of the top and the bottom. We don't want the negative, we want x to be some positive distance. So we take the square root and we get s over root 2. That's what x is. That's the base. And that's the height. So if you want the area of this triangle, we do 1/2 the base times the height. So we get s squared over 4, or 1/4 of s squared. These formulas will be helpful when it comes time to solve a cross-sectional volume question, because we need the area of the cross-section, and we times that, and we integrate that, basically. We times it by dx, a small thickness, and then we integrate that, and that's how we're going to get the volume. And so these formulas are handy, and we're just deriving the formulas so you don't have to derive them again. We'll put them on, you can place them someplace where you can easily find them. You don't have to derive them in the middle of a problem. The hardest of all these is trying to figure out the area of an equilateral triangle that has a side length of s. To do it, we go back to our familiar triangle here, the 30, 60, 90 right triangle. What's opposite the 30 is an x. What's opposite the 60 then would be that x times root 3. And then the hypotenuse is twice x. How's that going to help us? Because when we try to find the area of this triangle, we have to find the base and the height. This guy is the base. The base is s. So we get the height by dropping down the perpendicular. What's nice about that is that it's a perpendicular bisector. It bisects this side to give us 2 s over 2 lengths here. At the same time, it bisects this angle. It's an equilateral triangle, so it's also equiangular. All the angles inside are 60. These base angles are 60. And this angle up here, the vertex angle, is also 60. But when we drop that perpendicular, it splits the 60 in half. It bisects the angle as well. So that's why we're looking at this kind of a triangle, because it is made up of two 30, 60, 90 right triangles. What are we looking for? We're looking for the base and the height. This distance here in this red dashed line. How can we get that height? Just focus on the 30, 60, 90 right triangle that's on the right here. Opposite the 30 is s over 2. Call that x. So then what we need is the height, and that happens to be opposite the 60. So we take that x and we multiply it by root 3. So we take s over 2 and multiply it by root 2. S over 2 and multiply it by root 3. That's your height. So you want to find the area of a triangle, you take 1/2 the base times the height. The base is s, and the height is s over 2 root 3. So 1/2 the base times the height. And then simplifies to become s squared times root 3 all over 4. Or root 3 over 4 times s squared. So you don't have to derive this formula anymore. You can just use it, have it handy somewhere that you can quickly get to it. All of the cross-sectional volume questions involve finding the area of a slice, and the slices end up being small cylinders, and this is the area of the base, and so we're going to need these formulas. Here they all are in one place. The area of a square that has side length s, that's just s squared. The area of a semicircle, that diameter length s, we found out pi over 8 s squared. The area of an isosceles right triangle, where the leg is s, just half of s squared. But if the hypotenuse is s, we got 1/4 of s squared. And then finally, for an equilateral triangle, where the side length is s, we got root 3 over 4 s squared. Keep these handy. When it comes time to find volume by cross sections, it's useful to have these guys.